to the afternoon session. We'll start, as always, we have 3 talks, so we'll start with the first talk by Nadia Bihari Padhan, who's going to tell us about laminar, turbulent, and active flows in the Cahn-Hilliard-Navier-Stokes equation. So you still have a few seconds, but please take it away.
Thank you, Rika. So let me begin by thanking the organizers for giving me the opportunity to present my work over here. So I'm going to tell about the Cahn-Hilliard-Navier-Stokes framework for multiphase fluid flows, laminar, turbulent, and active. So I want to thank the collaborators, Rahul Pandit, Dario Vincenzi, and KV Kiran. So this is the outline of my talk. I'll begin with examples of multiphase flows. Then I'll give the framework for the CHNS, and I'll give 5 different examples that we use CHNS framework to explain varieties of phenomena in multiphase flows. The first one is the interface-induced turbulence in viscous binary fluid mixtures. Basically, here we uncover a new kind of turbulence in binary fluid mixture without the presence of inertia. And second one is the spatiotemporal evolution of liquid lens coalescence. Here I'll use 3-component CHNS framework. Then I'll talk about turbulence and coarsening arrest in active scalar fluids. Basically, we study turbulence in active model H, and we found some similarities with the conventional 2D Navier-Stokes turbulence, inertial turbulence. Then I'll talk about activity-induced droplet propulsion and multifractality, and we use 2 scalar order parameters to explain self-propelled droplets. And then at the end, I'll talk about interfaces as transport barriers in CHNS turbulence. So these are the examples of binary fluid mixtures. The first one is oil and water emulsions. Then we have examples of coalescence of 2 spherical droplets. Then there are multiphase flows with 3-phase coexistence, and this is the example of ternary fluid mixtures where a bubble is passing through a liquid-liquid interface. And then we have active multiphase flows where a droplet is filled with E. coli bacteria and it undergoes random walk. So now I'll explain the CHNS framework, and also it is called phase field model or active or model H. And this model was described well yesterday by Kevin. So we begin with an order parameter phi, which is conserved, and we write down the free energy functional for it. And the first term is a double well potential with minima at plus and minus 1. And the second term is the interfacial free energy with sigma, the interfacial tension, and epsilon is the interface width. Then the order parameter phi is governed by the Cahn-Hilliard equation, and it is advected by a velocity field which is governed by the Navier-Stokes equation. And here is the inertia term in the Navier-Stokes equation. Then we have viscous term and pressure. Then we have a coupling term coming from the interfacial stress, and that can also be written in this form. And depending on the problem, whether it is externally driven, we can have a forcing which is external forcing. Then we consider incompressible fluids. Yeah, we solve all these nonlinear partial differential equations using pseudospectral methods in a periodic box of psi 2 phi. And we write high performance computing program using MPI and CUDA, and run all these simulations in many supercomputing platforms. So the first example is based on this work, and which is on interface-induced turbulence in viscous binary fluid mixtures. So here I'm considering the model H or CHNS framework with a forcing which is called cellular forcing, and the equation is written in vorticity formulation for 2 dimension. So this is the form of the cellular forcing, and we are going to inject energy at k equal to 4 wave number, and the flow looks like a cellular flow or a vortex crystal kind of structure. Then for the initial condition of phi, we take many droplets, and we choose the forcing such that the Reynolds number is well below the critical Reynolds number. And for this kind of forcing, we know the critical Reynolds number, which is derived in this paper by Goto and Yamada. So when we evolve this this process, then it goes to a non-equilibrium steady state.
Sorry, the critical REC is the critical Reynolds number for what?
For the Navier-Stokes equation with force.
For what transition in what geometry?
Okay. So if you have periodic boundary condition so you are going from laminar to turbulent flow, then REC is the kind of a critical Reynolds number. After that, you have the hydrodynamic instabilities. So we are kind of in a regime of laminar flow. So we start the flow, and we get a laminar flow, and then we are going to add droplets into it. Droplets of fluid. Yeah. That one is only for Navier-Stokes equation in 2D. Yeah, with periodic boundary condition. So below critical Reynolds number, the inertia is negligible, and if you see the movie, this is the plot of vorticity field, and it is overlapped with the black contours of the phi interface. And then here you observe there are events of coalescence and breakoff in the interfaces, and it basically disturbs that background laminar flow. And in the next slides, I'll tell about will quantify the form of this turbulence over here. So basically, there is no inertia cascade of energy is happening. The turbulent flow that we are getting is only due to the interfacial fluctuations, and such melting of the vortex crystal has been obtained in these papers by Parlekar and Pandit and Diamond also. So this is the main kinetic energy time series, and it's a fluctuating one, and here we do averaging for the energy spectrum from the velocity field, and it has a broad energy spectrum with an exponent which is near to 4.5, and similar kind of exponent has been observed in polymer solutions in cellular flow by Gupta and Pandit. And this is so here basically here we are injecting the energy at k equal to 4, but because there is no inertia, there is no energy transfer happening, because there is no energy transfer happening, but the the broad power law we are getting only due to the interfacial fluctuations. So here we write down the energy equation in Fourier space. Similar analysis was done by our previous speaker, Dhruva, in the context of elastic turbulence. So here the first term is the contribution from the inertia term, and then second one is the viscous dissipation. Then we have contribution from the interfacial stress phi field, and then we have forcing contribution. So in this plot, the T of k, that is inertia contribution, is 0 over here, and the contribution from the phi, which is exactly balanced out by the viscous dissipation over here. So then this is the plot of our, the PDF of the local dissipation due to the phi field, and one can get from the budget equation. So this is basically the rate of energy injection, then we have rate of energy dissipation, and the rate of dissipation due to the phi field. So if you look at locally this one, then it has broad tails in both the directions, both positive and negative. That means the interfaces are injecting energy as well as dissipating energy. So this is somehow linked to the events of coalescence and breakoff, and that is kind of sustaining the turbulent flow. And here is the transition. So transition fixture for different capillary number, and the transition is non-monotonic, and we observe periodic behavior, then chaotic, and again periodic, and there are different re-entrancement of chaotic behavior again. So that is the first part. Second example is based on this work, and it is on spatiotemporal evolution of liquid lens coalescence. Here is a schematic diagram of coalescence of two static lenses. So the droplets on liquid substrate that form liquid lenses, and when two such lenses close together, they form a neck in between them, and they grow, they merge finally. So this is a schematic diagram of the system. So we have three different fluids which are immiscible: fluid 1, fluid 2, fluid 3. And so we have three different kind of sufficiency and coefficients now: sigma 1, 2, sigma 2, 3, and sigma 1, 3. So then we define three conservable parameter C1, C2, C3 to describe three different fluids. So this is the free energy functional for this three-component system, and the detailed analysis has been done in this paper by Boy, and this basically a algebraic extension of the two-component system. Similarly, this is the coupled Cahn-Hilliard-Navier-Stokes equations for three-component system, and so in the initial condition, we are taking all the velocity field to be 0, and when we start with a droplet, circular droplet at the interface between two other fluids, and then we keep all the surfaces to be equal, then in equilibrium, it goes to a state and it makes a shape of a lens, and yeah, then we take two such lenses together close by, and this is from 2D simulation, and this is from 3D simulation. Then the neck that grows with time, and I'll show that neck growth follows power law with different exponents in viscous and inertial regimes. So this is for the 3D simulations. So to describe this dynamics, we define a non-dimensional number, which is Onnes-Jorge number, which is basically ratio of viscous to inertia and sufficiency. And here basically we have the neck height versus time plot for different Onnes-Jorge numbers, and for high Onnes-Jorge numbers or viscous dominated regime, it follows a power law T to the 1, and it makes a crossover to a different power law 2 by 3 in the inertial regime with low Onnes-Jorge number. And we observe the similar exponents in 3D as well. This is in 3D simulations. So there is a distinction in the dynamics of the coalescence in viscous regime and the inertial regime. So in the viscous regime in particular, the vortices that stick at the neck region actually, and in other way in the inertial regime, the vortices quickly travels across the interface, and you can see secondary and tertiary vorticity formations in 3D as well. So in 3D, this is the top view for the 3D, And in 3D, basically, we have, apart from the growth in the vertical direction, we have the growth of the neck in the horizontal direction, and that is WT, and that also grows with similar power law exponents, 1 and 2 by 3, and these exponents are consistent with the experiments in this paper. So in this coalescence process, we observe lens merger induced turbulence. So when in the inertial regime or in the low Onage number, so this is from 2D simulation, and this is from 3D. So with time, this is the energy spectrum that goes to a state with a broad energy spectrum in 2D and 3D as well. So even the simple system has a turbulent kind of behavior. So we also study the coalescence of asymmetric lenses. This is the asymmetric lenses, and in particular in inertial regime, what we observe is that the scaling exponent 2 by 3 that makes a crossover to another exponent 1 by 2, and 1 by 2 is very popular exponent for coalescence of spherical or circular droplets. So this geometry is in between the symmetric lens and the circular droplets.
So was the power law changing within 1 decade?
Here? Yeah, so actually because this is a tiny system, you have tiny droplet, you can't have a bigger one in the simulation. So if you want to see a long range of power law, then you have to make different simulations with different Onage number. Then you can have a broad range of power law that will explain for the lens coalescence. So with single simulation, you can't cover the entire range. So the example 3 is based on this paper, and it is on turbulence and coarsening arrest in active scalar fluids. So basically, we are going to look at the turbulence in active model H and active model H by Cates. Cates has already spoke about the active model H. So this framework is quite similar to the model H, except the stress term. We have an extra stress term in the Navier-Stokes equation, and this is the effective surface tension, and according to active model H, this coefficient can be positive or negative, and for negative value, that is for contractile systems, it shows coarsening arrest in the scalar alloy field. So this is the autoparameter field for activity minus 0.01, and you can see there is a coarsening arrest happening at a particular length scale. So basically, there is a diffusive growth for the coarsening, and because of the negative surface tension, it stops the domain growth. And when the activity is 0, that means it's converged to model B, and it is only the growth of the phi field is basically only due to the diffusion, and that grows with time with an exponent to the 1 by 3, which is the well-known Lipschitz-Shallow's exponent. When you increase the activity, then the coarsening gets arrested at a particular length scale, and that length scale decreases with increasing activity. So such coarsening arrest in binary fluid mixtures, as already explained in these papers, and but these systems are externally driven, but in this case, this is internally driven by the active stress. So here is the energy spectrum from the velocity field, and this is compensated with 5/3 exponent. So for high activity, all this the spectrum that converges into a 5/3 exponent. And let me remind, the 5/3 exponent is the inverse cascade exponent in 2D inertial turbulence, which is driven by external forcing. So here it is internally driven, and we observe a scaling exponent which is similar to 2D conventional turbulence. And when we increase the activity, the Reynolds number, which is defined in terms of the integral length scale from the energy spectrum, that also grows with activity. So here the contribution of different terms. So this is the energy equation in the Fourier space, and the first term is the contribution by the inertia, and then we have the contribution from the friction term, and then we have viscous dissipation contribution, and then we have the active stress contribution. So for the low activity, you can see the inertia is negligible, and the contribution or the energy injection from the phi field is exactly compensated by the viscous dissipation. But when we increase the activity, then we are activating actually many Fourier modes, and also there is an activation of the nonlinear term over here. So the 5/3 exponent that we are getting is kind of more or less dominated by the interfacial stress. So basically we made a check that even if you remove the inertia term from the whole picture, then also the 5/3 exponent preserves, and that is due to the whole turbulence is happening only due to the active stress in this particular system. This is an example of based on this paper, and this is on activity-induced droplet propulsion and multifractality. So here we consider two conservative parameters, one phi, which represents a binary emulsion droplet, and it is defined evolved by model H, and we have active scalar parameter psi, which represents the composition of the active matter, and that is evolved by active model H. And basically we try to combine two model over here, and we write down the combined free energy functional in terms of phi and psi. So the first two terms are the similar terms, double well potential, and we have an extra coupling term which is beta phi psi. So we consider beta to be greater than 0 to make sure attractive interactions between phi and psi. And these are the coupled Cahn-Hilliard-Navier-Stokes equations for phi, psi, and this is the Navier-Stokes equation, and we have a friction term over here. So I'm going to show the results in particular to 2D. And we have passive stress that is coming from the passive or parameter phi, and we have an active stress from the active order parameter, and we have a coefficient sigma 2 tilde, which is not equal to the diffusive sufficiency. So it is based on active model H, and as I described in the previous example, that when it is negative for the contractile systems, it shows arrested phase separation. So we define different non-dimensional numbers to study the dynamics. This is the Reynolds number based on the radius of the droplet. Then we have Peclet number, and then activity parameter, which is the ratio of the mechanical surface tension in the active field and the diffusive surface tension. So when activity is 0, so this is a picture of the the active field psi, and the magenta line is, it represents the droplet interface. So for A equal to 0, basically we are decoupling into model H, and it goes for complete phase separation, where if we increase the activity to 0.15, then the phase separation of the active order parameter get arrested, and the droplet propel in a unidirectional direction. So let's further increase the activity over here. Then if we increase the activity again, then the droplet undergoes chaotic propulsion, and look at the Reynolds number, which is near to 0. And in the chaotic propulsion, if you look at the interface, then there are huge amount of fluctuations in the interface. So with increasing activity, we observe static to unidirectional to chaotic propulsions. So the unidirectional propulsion is driven by the vortex dipole, as you can see from this plot of velocity vectors coupled to the vorticity field, and this is the droplet interface. Then it propels in a single direction. The chaotic propulsion is driven by the active turbulence that I described in my previous example, and we have here a broader energy spectrum in the velocity. So this is the droplet center of mass trajectories. So for low activity, it is a straight line, but for higher activity, it shows a chaotic kind of trajectories. And if you look at the mean square displacement, then it shows a super diffusive behavior with different exponent 4/3 and 5/3 depending on the activity. So now we look at the interface deformation. So we define non-dimensional measure of the interface deformation, and this is the deformation with time that looks very fluctuating, and actually this is a multifractal time series, and such multifractal time series has been observed in our climate systems and many chaotic systems. So this is the multifractal spectrum for this time series, and for high activity you see a broader multifractal spectrum. And if you compare to a fractal time series, then that is basically a tiny point in the whole spectrum. So this is basically happening in the Reynolds number regime, but there is a study by Rahul Pandit in this paper that for high Reynolds number flow, and which is externally driven, and the droplet interface fluctuations also show multifractal behavior. So there is a somehow a similar behavior over here, even if it is a low Reynolds number flow.
Before you go to the next topic, in your directionally propelled drop, you just go back one more. No, the previous, the one that is not, the one that's propelling unidirectionally. Did you measure the flow field in the outside?
Oh, in the flow field. Okay. So we have not measured explicitly, but that looks very tiny actually. It's very almost zero.
Oh, I can see it here actually. So it's basically it's a movie.
This one. Okay.
I see. Okay, so it's. I guess it's a dipole, post-dipole swarm.
Yes. Once the dipole forms, then it moves.
No, the field in the outside. Yeah. So I guess it's that four-roll-like thing. I don't quite see it. I guess it is. Okay. I'll check.
What are these jumps actually of the vortices back to the back of the droplet every so often?
Okay, so that is you can correlate with this thing. So there is a tail which is doing this kind of motion, and it is perfect. So this is the final example, which is based on this work. It is on interfaces as transport barriers in CHNS turbulence. Again, we are considering the model H dynamics, and this is in 2D. So we have a friction term, and we have a forcing. Now we are taking the column over a forcing, but now the Reynolds number is quite high, which is quite high compared to the critical Reynolds number, and we use many tracer particles, 10 to the 5 number of tracer particles into the flow, and the tracer particles basically it only follows the background velocity field. So in the first row, so we have a turbulent flow, and we initiate tracer particles at the middle of the system. Then what we observe is that the particles disperse very quickly into the flow, as you can see in the movie. In other two cases, what I'm going to do is we are putting the tracer particles inside a droplet, and that is also moving with the same velocity field, turbulent field. Then those tracer particles stays inside the droplet quite significant amount of time before they're going out of the system. So basically that is almost 300 times longer compared to the system without droplet interface. So here it is, one thing is clear, that the interface is acting like a transport barrier for these tracer particles. Then we look at the number of tracer particles inside the droplet divided by total number of particles with time, and it decays exponentially for all radius of the droplets. And that decay time that grows as the radius to the power 3/2. So basically particles spend more time in larger droplets compared to the smaller one. So to confirm this, we saw the PDF of the cosine of angle theta. Theta is basically the angle between the velocity vectors and the normal to the droplet interface. And what we observe is that for small droplet, the particles tend to align perpendicular to the interface, and they are coming out. But for the larger radius, the particles prefer to align parallel to the interface. Basically, there is a shear kind of flow happening near the interface, and it shows in this PDF. So that's the end of my talk, and this is the conclusion. So we have demonstrated that the Cahn-Hilliard-Navier-Stokes framework offers a robust theoretical foundation for probing diverse aspects of fluid dynamics, both laminar and turbulent, across binary, ternary, and active fluids. So I provided 5 different examples where we can use the CHNS framework very efficiently. And we are currently also working on different active matter systems using such framework. So thank you very much for your attention.
All right, thanks for the talk. It's very early, so we have a lot of time for questions. I can actually start with one. So you said that the Reynolds number increases with activity in your case.
Yes.
Can you explain why?
So basically, you are injecting more energy into the system, and your integral length scale, which is based on the energy spectrum, that is increasing actually, because your turbulence is kind of increasing in some sense.
So it just drives stronger flows.
Yeah, driving stronger. So it is kind of activating more Fourier modes in the energy spectrum.
You can show the plot also and the definition of the length.
Yeah,
Go
so
to
that is.
slide.
Yeah, that is based on the integral length scale. So this is the integral length scale defined from energy spectrum. So actually it is increases when you use the coarsening arrest length scale also in this case.
So you, sorry, go ahead.
Just to follow up on what you were saying, what does grad free look like? I mean, in the sense that the injection length scale is coming from the grad free term in the flow equation, right?
Yes, yes.
What does that look like when you're in this steady state?
You mean the contribution? This one is
Active stress.
yeah. This is active stress contribution in Fourier space. So that has, you know, it shows it is injecting energy in different Fourier modes. So for low activity, it's kind of here. So there is no energy over here. So
Is there some cheap way for me to think about what is 10 in this wave number in terms of physical length scales, standard model H length scales?
So this is basically box 2 pi cross 2 pi. So 2 pi by k maybe 2 pi by 10 that length scale, physical length scale. So this is slightly bigger length scale in the real space.
I mean, in the sense that if I take active model B,
Okay.
then I have an interface length, then I have a
Okay. Compared to the
compared to
coarsening,
characteristic length scales that are there in
coarsening
model.
arrest length scale. That I have to check actually how it is related to the coarsening arrest length scales.
So you have turbulence present in your transport barrier study, correct?
Yes.
So how does the shear near the surface of the bubble that you mentioned, how does that compare with the characteristic shearing of the turbulence in the simulation? Stronger, weaker, the same?
So that I think one can do with the Okubo-wise parameter to show
Right.
the strain and vertical dominated region. So I don't have plot now. I can show you.
It would be interesting to see that.
So basically, in Okubo-wise parameter, if you look at the PDF, then that has a long tail. If you have bigger
Sure.
droplet.
But I mean, Okubo-Weiss really tells you more about the structure of the flow, right? Shearing, shearing versus closed vortices,
Yeah.
kind of thing. It would be, even if you have shears presence, it would be interesting to know the shear near the barrier versus the typical shear in the turbulence.
Okay. Actually, we have compared that, and I'll show you the
Yeah.
plot. Thank you.
Please.
Yeah, Nadia, is there a way of thinking of your moving drops in terms of a dynamic Berry phase or something like that?
I don't know. I have to think on that.
Dynamic, what, Berry?
Very.
Berry phase.
Dynamic Berry phase, never saw it. I think.
So you mean, sorry, you mean like it does a periodic non-reciprocal
Yeah.
deformation and as a result?
Yeah. But not slow, it's dynamic.
Ah.
Well, it's a low, it's mostly a low balance.
I had another question about this actually. So do you then interpret this increase of the Reynolds number as the cause of just the activity driving inertial turbulence? Is that how you interpret the spectra?
So say it again.
I'm wondering whether the activity is somehow driving inertial turbulence, and that's how you interpret the Kolmogorov power law.
Yeah, that is not driving the inertial turbulence. So even if you don't have inertia, and that gives this spectrum.
So what interpretation do you give to
So-
this result and this
So
experiment?
basically, one way is the active stress is injecting energy at those particular wave numbers, and it is itself creating the energy spectrum. In detail, if we want, then we need to look at the flux for the active stress, how that is distributing energy among nodes. So, but there is no inertial cascade happening.
More questions for Nadia? All right, if there are no more, then we still have time, but I propose we move on to the next talk, and then we can just have a longer coffee break. So let's thank Nadia.